an experiment.
We don't know yet.
Why is light so fast?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, why the brightness of a satellite is concerning astronomers,
the last meal of a 400 million year old trilobite,
and the latest on the winners of this year's Science Nobels. I'm Nick Petrichow.
And I'm Benjamin Thompson.
There's a reason that a lot of observatories are a long way away from cities. Light. If you're trying to look at something very far away, very dim, or both, then light pollution is something best avoided, or you risk obscuring what it is you're looking at. But in recent years, light has become hard to avoid. That's because our skies are becoming increasingly crowded by bright satellites.
So, bright satellites aren't necessarily a new thing.
This is Michael Brown, an astronomer from Monash University.
The International Space Station has been around for over 20 years now, and it's spectacularly bright, and lots of people, perhaps listeners to the podcast, have gone out and looked at the space station passing overhead. But what's really taken off in the last couple of years is the number of satellites in low Earth orbit. So a couple of years ago, or a decade ago, there were less than 1,000 active satellites in orbit. Now there's more like, I think it's a moving target, but I think it's around about 8,000, and that number's increasing very, very rapidly.
These satellites don't produce light, but they do reflect sunlight back down to Earth, and that risks obscuring astronomers' observations, etching bright trails across images astronomers are trying to gather from ground-based telescopes. And if the thing an astronomer is trying to look at is behind one of these streaks, well then, satellites have just made their life a little bit more difficult. And there has been particular concern about one satellite known as Blue Walker 3. Michael wrote about some of these concerns shortly after it launched at the end of 2022.
This particular satellite, Blue Walker, was this sort of great big antenna, and it happened to be spectacularly bright, sort of comparable to some of the brightest stars in the night sky. And, their sort of plans are talking about 100 or more of these satellites of this sort of brightness. And so, there is a concern that a lot of satellites could be up there.
Around the same time, the International Astronomical Union also issued a statement about their concerns. In it, they recognise that the new satellite constellations have an important role in improving worldwide communications, as such satellites can provide mobile communications in remote areas. But they said, quote, their interference with astronomical observations could severely hamper progress in our understanding of the cosmos. But how bright is Blue Walker 3? Well, a new paper in Nature is presenting new data gathered over 130 days by a swathe of amateur and professional astronomers from all over the world, with the most comprehensive answer yet. Astronomers measure brightness using a scale called apparent magnitude. Now, this is a carefully calibrated logarithmic metric, but for the purposes of this podcast, all you really need to know is that the lower the number, the brighter the object. Here's one of the study's authors, Jeremy Tregloan-Reed, on Blue Walker 3's magnitude.
The initial observations before it began to unfurl, or basically began to unfold, was that it was around about magnitude 6, magnitude 5. But then after it started to unfold, we suddenly measured a stark increase to magnitude 1. And in some of our data, we actually measured it to be magnitude 0.4.
Magnitude 0.4 would make it one of the brightest objects in the night sky. For astronomy buffs listening, that's around the brightness of the stars Procyon and Arcana. It is important to note that this did vary, but nonetheless, at times it was hundreds of times brighter than the current International Astronomical Union recommendations. Now, astronomers do have tools to deal with bright satellites. The International Space Station is, by all accounts, brighter than this, and astronomers have dealt with it for decades. Machine learning can be used to paint over the satellite streaks, and there's also a method known as dithering, where the telescope is shifted ever so slightly between exposures so that if you have a bright satellite streak across one of the images you take, it's possible to essentially erase it out using the others. But several companies, including the one behind Blue Walker 3, are planning to launch constellations of satellites, great groups of satellites, sometimes numbering into the thousands. And according to Jeremy, if there are a lot of these bright satellites, even with these tools, astronomers' jobs are going to become much harder.
The problem is if you've got a wide enough field of view, then potentially you can have a streak in one, another streak in another streak in another, or 2 or 3 streaks in each one, and the whole thing gets a lot messier. But even if you were to do that, then instead of having a single exposure of, say, 300 seconds, you now need 4 or 5 300-second exposures, which means instead of looking at, say, 20 galaxies in your night, you're only looking at 5, which then increases the amount of time people will need to do their science, which, considering the finite number of telescopes and instruments, that will basically reduce the number of proposals that can get accepted, and so therefore slow down the amount of science that we can do.
The company behind Blue Walker 3, AST Space Mobile, told Nature that to address the concerns that astronomers have, they are collaborating with NASA and certain astronomy groups, that they will use specific flight manoeuvres to reduce magnitude, and they are planning to equip their next generation satellites with anti-reflective materials. Nonetheless, there are several companies that are planning their own constellations of potentially bright satellites, and there is little regulation on how bright they should be. And while some of these companies, like AST, are starting to collaborate with astronomers, Michael, who you heard from earlier and who wasn't involved in the new study, thinks that more is needed.
I think collaboration is good, and it's good that it's starting to happen with some of the companies, but I think you do need a regulatory framework, because collaboration, you only need someone to be a bit selfish and not collaborate, and you've got real problems. So a regulatory framework would be good. Some testing of the satellites to make sure that they do meet certain guidelines in terms of how much light they reflect towards the ground would be very, very useful. And keeping satellites, their orbital parameters up to date so that we know exactly where they are in orbit, so that telescope observations can be scheduled around them, would be particularly useful. And then also, and this is sort of a broader issue, once a satellite stops working, making sure that you get it out of orbit as quickly as possible so that it's not at risk of colliding with other objects, etc. So, wanting to get rid of the crap from low Earth orbit as much as possible, I think, is really a critical part of it too.
Michael and Jeremy also spoke about the importance of our shared heritage of the night sky. For millennia, people have been able to look up and observe the wonder of the cosmos. But will increasing numbers of bright objects orbiting the Earth change this? According to Jeremy, there's a lot more than astronomy at stake.
It's not just astronomy that's potentially impacted, it's potentially wildlife, nocturnal birds or insects that migrate at night, and potential also cultural heritage and religions that particularly use the night sky for their particular practices. So, at the end of the day, we're not saying no to the satellites. I know some people in astronomy are saying no to the satellites. My attitude, at least, is basically, we all need to share the night sky, but we've got to do it in a way that it doesn't impact other people.
That was Jeremy Tregloan-Reed from Universidad de Atacama in Chile. You also heard from Michael Brown from Monash University in Australia. For more on that story, check out the show notes for some links.
Coming up, how researchers peered inside a 400-million-year-old fossil to identify the last meal of a trilobite. Right now, though, Shamini Bundell is here with this week's research highlights.
How did the carrot get its colour? A new study of carrot genetics might provide some answers. It seems the carrot was first domesticated in Asia in the 9th and 10th centuries. Back then they were generally yellow or purple in colour. Orange and red varieties arose much later, probably in Western Europe in the 16th and 17th centuries. Studying the genes of different carrot varieties made researchers think that orange carrots may have first arisen by crossing yellow and white varieties together. The new carrot reference genome also shows how selective breeding has impacted the genes associated with root size and shape, taste and colour, and a later flowering season, which is important because the taproot, in other words, the part we eat, tends to become woody once the plant has flowered. More recently, the role of carotenoids in reducing vitamin A deficiency has likely made orange carotenoid-filled carrots even more popular. Crunch on more of that healthy research at Nature Plants. Researchers have discovered how a type of synthetic diamond is able to stay strong. It can heal itself. Diamond is the hardest material in the world, but it's also brittle. Put it under enough pressure and it cracks. This can be a problem in diamond's industrial uses, such as in mechanical tools for cutting and drilling. But now researchers have put a particular type of synthetic diamond under the microscope. It's called a nanotwinned diamond composite. It's known for being tougher than normal diamond, but under the microscope, researchers saw something even more intriguing. Small fractures and fissures in the material could self-repair, with carbon atoms forming new bonds across the gap. This self-healing allowed the synthetic diamond to recover a third of its tensile strength, which could allow scientists to design future diamond tools to be at least partially fracture-resistant. Bond with more of that research over at Nature Materials.
Trilobites are a group of extinct marine arthropods, distantly related to animals like crabs and spiders. They look a little bit like underwater woodlice or pillbugs, protected by a 3-part armoured exoskeleton. And they were a pretty diverse group. Some of them were the size of a grain of sand, some longer than your forearm, and they lived around 520 to 252 million years ago. We know this because absolutely loads of trilobite fossils have been found all over the world. As fossil animals go, they're pretty iconic. But while trilobites might be fossil famous, there's not much known about these animals while they were alive, in part because the soft parts of their body don't fossilise well. They were so abundant that trilobites were likely a big part of marine ecosystems, but what they were doing is shrouded in mystery. But perhaps that shroud has been pulled back a tiny bit. A discovery in a Czech museum has yielded insights into the life of one of these animals, from the species Bohemelicus in Kola. Specifically, a team figured out what it ate just before it died over 400 million years ago. This finding was published in a recent Nature paper, and I reached out to one of the authors, Per Ahlberg, from Uppsala University in Sweden, to find out more about the work. He explained why working out what trilobites like to tuck into has not exactly been straightforward.
I couldn't tell you how many fossil trilobites have been found over the years, but it must be in the tens or more likely hundreds of thousands of specimens. And yet, for all of that, no stomach contents with anything identifiable in them have ever been found. And this, of course, is a pain, because if you want to understand an animal, one thing you want to know about it is, well, what did it eat? And here we have these really abundant, obviously important animals. You have them for like a couple of 100 million years early in the fossil record of animals. No stomach contents. Just nothing you can say anything about.
And this question then of what a trilobite might have eaten is one that you've answered in this paper. And it comes down to a particular fossil found in this little rocky ball, this little nodule a few centimetres across that had been cracked open. Tell me a little bit about it.
So the particular fossil here is a trilobite in a nodule found in a ploughed field near a town in the Czech Republic, and it was found in 1908, as far as we know. It's 465 million years old, and it's been in a museum for more than a century. Now, this particular fossil had caught the eye of Petr Kraft. He's the first author of the paper. He's a paleontologist at Charles University in Prague, but it had caught his eye when he was a kid. And he'd been wondering about this for like several decades. And it's clear when you look at the specimen that there's something inside. The shell's a bit broken, and you can see that there's a strand of smaller bits and bobs going down the middle of the specimen, looking like there could be a gut fill. But how on earth do you get any information out of that without breaking and ruining the specimen? Well, it so happened that I'd been working for some years with very high-grade tomographic X-ray scanning of fossils at a synchrotron in Grenoble in France. And we decided, I and my colleagues, to take this specimen to be scanned there to see whether it would allow us to see what the contents of the gut were, without damaging the fossil. And it came good. We were able to identify just about every fragment of shell. So all of a sudden we could write down effectively the complete menu of this long dead animal.
So you use the powerful X-rays then in the synchrotron to kind of peer inside this fossil and the rock it's encased in. So what has it shown you then? Is it like indentations of the menu?
So what you had to start with was the trilobite, and in its gut you had lots of little bits of shell. Now, much later after it died, like millions of years later, because of water circulating through the rock, the original shell of the trilobite and also all these little shelly bits in its gut were dissolved away. So there are only holes in the rock now, only voids in the rock. But they, of course, perfectly retain the shape of the things that were there, and they show up very clearly in the scan. Most of the gut contents are entirely enclosed within the rock. And so we're able to model out fully in 3 dimensions each of these little bits, clearly showing where the gut was.
So you've got a several 100-million-year-old Last Supper for this trilobite then?
Yep.
And so you can see then by looking at the pattern of these fragments of shell, you can infer what that dinner might have been. What's the story there of the sort of things that you found?
Right, well, we're finding several different kinds of animals. On the one hand, ostracods. These are like sort of millimeter-long little swimming crustacean shrimpy things. They still exist today. You've got a sort of a now extinct kind of echinoderm called the Stylophoron. It's a little sort of, again, shelly bottom-dwelling thing. Yet another group of animals, things called hyolithids, they're just totally extinct today. They look like little living ice cream cones with a sort of animal inside. And we also got a little clam shells and whatnot. All of them quite small.
It seems like quite a varied diet then of different things. It's not just selectively eating one type of animal. And you got the contents of its stomach then, these shells. What have you inferred about the actual way that this trilobite lived its life, do you think?
Well, you have this animal, it looks rather like a big woodlouse. And on the other side of the trilobite, there are many, a couple of dozen pairs of legs. And it spends its lifetime walking along the seafloor, searching for small animals lying on the mud. But it seems to be a really uncritical feeder. It just sort of shovels them into its mouth. The mouth, of course, is on the underside of the animal, fairly near the front, and it's using probably the basis of its front pair of legs, which have spikes on them, to rip up the food a bit, shove it into its mouth. And just before this poor thing died, it had really been eating seriously large amounts of food. It had been absolutely shoveling it down, and it may be that it was doing so because actually it was about to shed its shell, like arthropods do. And we know from modern arthropods, the animal inside has to sort of swell and crack the shell, and they often do so by either swallowing lots of water or in some instances air to expand their gut, because it's a good way of making the whole animal kind of swell up. So maybe it's doing something like that. Maybe this kind of what looks like frantic overeating is actually to do with getting ready to molt and shed its shell. But at any rate, over the last few days, it's really been shoveling it down.
So I think you got a sense then that this trilobite was a scavenger.
Mm-hmm.
What was presupposed about this animal then, and how does your work fit in, and how does it maybe compare to modern arthropods, say?
Not that much was presupposed about, and to be honest, because if you just got the sort of upper shell, it really wasn't easy to say very much. One really interesting thing that's come out of this, and a quite unexpected bit of information, concerns its digestive physiology. You see, the shelly bits that it has swallowed, we know what kind of shells they are, and we know from other fossils that those shells are made of calcium carbonate. If you pop a piece of calcium carbonate into strong acid, it dissolves very quickly. But we can see that in the trilobite that hasn't happened. The bits, even at the back end of the gut, are just as jagged and sharp and well preserved as the bits near the front end. So they haven't been dissolved, they haven't been etched. So clearly then, interior of the stomach was not acidic, it was at a kind of neutral pH, more or less, or maybe even slightly alkaline. All right, how does that compare with modern arthropods? Well, the answer is it compares very well. Not all that many arthropods have been looked at, but when they have been looked at, that's what they show. And if you look both at modern crabs, which are crustaceans, and modern horseshoe crabs, which are spider relatives, and so very distant from true crabs, they have this kind of basically neutral pH gut chemistry. So it looks as though that style of gut physiology was established really early on in these animals. So it points to great stability in the digestive physiology of marine arthropods.
I mean, with any fossil-related paper, of course, you've put forward your evidence, and maybe people will look at it and take different influences. What questions do you think that other researchers might have?
The identification of what things been eating, I think, is straightforward. I don't think any colleague with experience in these groups will look at these and say anything other than, stanopherans, hyalithids, ostracods, these are entirely familiar sort of organisms. The gut physiology thing, there are always going to be people who go, "Ooh, you're overreaching here with your inferences." But the fact of the matter is that the condition of the shells as you travel down the gut really tells you that the gut pH is neutral, because otherwise they couldn't look like this. But of course, we will have to see what people say.
Of course, it has to be said, Per, that this is n equals 1, right? And of course, trilobites range in size from, 1 millimetre long to almost half a metre in size.
Yeah.
And lots of different kind of body morphologies and so forth. I mean, do you think this is potentially characteristic of the broader trilobites, or is there more to be discovered, do you think?
Now, there, of course, we have to be really careful. I would say, in fact, there's a high likelihood that this guy is not representative. Firstly, because just as you say, you've got this huge morphological diversity, and of course they were doing different things, even if we don't know what those things were. But also, precisely because it is the only trilobite that has turned up with shelly material in its gut, makes you suspect that perhaps that's a fairly unusual thing to be doing. But I think what's really wonderful with this technique that we're using, synchrotron tomography, is that you can study a specimen like this without damaging it. And now, given this technique, there's a definite opportunity here to pursue this kind of investigation systematically and speculatively, because you're not always going to know. And you're going to be scanning a bunch of trilobites and going, nope, nothing in that one, no, nothing in that one. But, it can't be helped. There's no other way of getting at this. And hopefully it will gradually, on that basis, be possible to build up a broader picture of what these things were up to.
That was Per Ahlberg from Uppsala University. To read his paper, head over to the show notes for a link. It's Nobel's week this week, so as is tradition here on the Nature Podcast, Flora Graham, senior editor of the Nature Briefing, joins me to discuss this year's science winners. Flora, I think this is the 4th year in a row we've done this now. How are you doing today?
It's great. I love it every year, to be honest. I know maybe some people have become a little bit cynical about the Nobels, but for me, it is always a treat to discover more about individual scientists. And I know that science comes from great groups of people and huge sways of invention. But every time I discover the stories of these individual scientists, it is just endlessly fascinating.
Well, let's kick on then and talk about the winners this year. And I think we should start, as is traditional, at the start of the week on Monday, and the Nobel Prize in Physiology or Medicine, which was awarded to Katalin Karikó from Szeged University in Hungary and immunologist Drew Weissman from the University of Pennsylvania in the US. And they've won for discoveries that enabled the development of mRNA vaccines. And of course, mRNA vaccines were instrumental during the COVID-19 pandemic.
There's so much I love about this story, not at least the incredible, success and triumph of the vaccine development to fight the COVID epidemic, which saved countless lives and countless serious illnesses. But even beyond that headline, the fact that these two scientists were both somewhat stuck in a backwater of research at the time. They met at the photocopier in the queue back in the old days before the internet, when if you wanted to keep up with the literature, you had to find it at the library and queue up and kind of battle for space at the photocopier. And the fact that they realized that they both had very complementary skills to push this field forward, really against a lot of the odds and against a lot of discouragement.
Well, let's talk about what they were actually working on then. So mRNA, messenger RNA, then obviously a key part of gene expression, but it actually has been kind of piggybacked then to make vaccines. The idea being that injecting mRNA could deliver the instructions to make something that the immune system could recognize and attack, a protein from a virus, say.
And this was seen as a very promising technology, and yet this RNA just could not function within the body. It was triggering an unwanted immune response. And what they did is they found a way to swap a molecule, to modify this RNA, to change its genetic material with a similar one that would not trigger this unwanted immune response. And this just opened the door not only to vaccines against COVID, but really a huge movement that's going on right now in clinical science, looking for vaccines against HIV, influenza, cancer, malaria. There's a feeling that there's a huge amount of potential moving forward.
And one of the Nobel Committee members is quoted as saying, this discovery has opened a new chapter for medicine. But I think it's worth saying that, of course, there is one part of this development of the vaccines, but a very, very important part nevertheless.
Yeah, I mean, as happens every year, and I think we all know, Kariko really emphasized and has always emphasized that this is part of a much broader field with many, many scientists working very, very hard to move the field forward. It could be seen as a criticism of the Nobels, but the impression I get with this one is that, you know, there's a lot of positive reaction from the scientific community.
And very interesting stories for both of their careers as well.
Yeah, very interesting. I mean, Kariko in particular, she actually grew up in Hungary with no electricity, no running water. Her family relocated to the US. She hit some serious career setbacks. I mean, a lot of people have been noting that the University of Pennsylvania has been congratulating her and Weissman. They were both at the University of Pennsylvania when they met. And yet, they demoted her when, you know, she just couldn't bring in the grants to support the research that she wanted to do. So to see her not only win this prize, but also Kariko and Weissman won the Breakthrough Prize, one of the most lucrative prizes in science in 2021. As she said, you know, it wasn't warp speed, her success, but it certainly is coming to fruition in huge terms.
And what about Weissman then?
To me, what I found interesting about Weissman is he is a classic scientist in one way, which is he's somebody that his colleagues and his family say he just loves pure research. He's known even by his own family members as being a very quiet, reserved person, but he's clearly got the passion for research inside him that's allowed him to drive this forward for many years. And what he has said is to see this research actually helping people, that's the dream that he had, and that's what he's seen come to fruition.
Well, let's move on to Tuesday then, and the Nobel Prize in Physics, which this year was awarded to 3 scientists: Pierre Agostini at Ohio State University in the US, Ferenc Krauss at the Max Planck Institute for Quantum Optics in Germany, and Anne L'Huillier at Lund University in Sweden. And this is for their research into attosecond pulses of light.
Yeah, these are ultra-fast laser pulses that are able to image things at unbelievably tiny scales, much smaller than we would have thought possible otherwise. And as you can imagine, this has applications across chemistry, biology, physics, across all of science, really.
I mean, it's difficult to get a sense of scale sometimes, but a fact doing the rounds is that there are as many attoseconds in a second as there have been seconds in all time since the Big Bang. So we're at the sort of far end of the tiny scale here. I think a quintillionth of a second, which is, I mean, my goodness, it boggles the mind a bit.
It's absolutely amazing. And the impact of this is really hard to overstate. Krauss himself gave some examples when he spoke to Nature Photonics last year. He talked about some of the amazing experiments that have become possible because of these techniques, like direct access to the decay of atoms, electron tunneling, even the migration of electrons within molecules can now be directly measured in a way really not thought possible before.
Yeah, because these ultra-fast waves are kind of, I suppose, like a very fast strobe light, which gives these kind of snapshots in obviously a tiny amount of time, so you can see things like this. But it seems like the story of attosecond science began with L'Huillier in the 1980s.
Yeah, its origins apparently come from when L'Huillier was studying ionized argon, and when they exposed it to infrared laser light, they found that it actually produced photons in a series of higher frequencies than the laser light that had triggered them. And that kind of opened the door for this incredibly interesting area of what they call the overtones of the laser light.
And it seems then that Agostini and Krauss did some important work translating those into attosecond pulses. And these attosecond pulses are getting shorter and shorter. I read that Krauss produced one that lasted 650 attoseconds at the start of this millennium, but that is getting less and less as time goes on.
I think one of the fun moments from this Nobel story that I really enjoyed was the fact that Lulé was in the middle of a lecture at London University where she teaches when she got the call. Now, apparently what happened was not that she had her phone on during the lecture, but there was a little break in the lecture and she saw she had like 1 million missed calls and all the students gathered around and were like really excited when she took the calls. And then she finished the lecture. She gave the second half of the lecture. I mean, how's that for dedication? She just says, well, teaching is very, very important.
You have to respect her for that, but I'm sure her mind was potentially elsewhere. But I know that you and I like to have our favourite How Did You Hear story, and that is the best one this year.
And it might be worth noting that Anne Lhuillier, she's only the 5th woman ever to have won the physics prize. Marie Curie was back in 1903. We didn't get the next one, Maria Goeppert-Mayer, until 1963. And yet Donna Strickland won in 2018. Andrea Ghez in 2020. So it does seem like the graph is pointing upwards in that department.
And there is an infographic showing the imbalance in prize winners in the news stories that we'll link to in the show notes. But finally, let's talk about today's prizes, which were announced this morning, and that's the Nobel Prize in Chemistry shared between 3 researchers: Munji Buendi at the Massachusetts Institute of Technology, Louis Bruce at Columbia University, and Alexei Ekimov at the company Nanocrystals Inc., and they're all in the US.
That's right, and apparently this Nobel was leaked by accident. The Nobel Committee sent out a press release to Swedish media a little bit early, but because the winners were all based in the US, sounds like it didn't ruin the surprise. We definitely know that Buendi said he was sound asleep when the call came in. And they won for quantum dots. Now, these are tiny molecules, tiny semiconductor crystals. They're just a few atoms in size. And they have some properties of single atoms that actually let them be tuned so that they can emit very specific wavelengths of light. And this ability is very useful in applications that benefit from this very precise wavelength of light.
And again, these are prizes that were several decades in the making. The story here starts again in the early 80s. And Ekimov, who was looking at glass containing copper chloride particles and figured out that different sized particles led to the glass being different colours, as I understand. And Bruce was doing similar work using quantum dots in a solution. And Buendi actually developed a way to make them at specific sizes. And when you excite them, say with UV, as you say there, they give out light at different colors, which allows them to be used for different things.
Yeah, this is one of the areas of research where the picture really does help bring the story to life, because you get a lot of these gorgeous images like we have in our story on Nature of flasks beautifully illuminated with UV light showing a rainbow of colors emitted by quantum dots, which we see now in multi-million pound industries of computer displays, televisions, and things like that. So this is definitely a technology that you can see and experience for yourself.
Yes, absolutely right. Expensive televisions are one avenue for this research, but also I've seen them being used in like medical imaging and stuff, and they give out this super bright light, which is very, very useful, and potentially even in things like solar cells as well.
And a similar concept has been adopted as a platform for quantum computing. So this is about fabricating devices on a silicon chip that have the properties of quantum dots, and then manipulating these quantum properties, the spin of the individual atoms that are trapped inside them.
And let's tell one more story then about how the researchers heard that they'd won. In this case, it's Buendi. When he was asked in the press conference live, how do you feel about it? He said very surprised, sleepy, and shocked. I guess it was first thing in the morning for him in the US.
Buendi did say that not only was he surprised because he was asleep, he was surprised because he said, he didn't think it was him that would get the prize, because there are such a lot of people in the field who have contributed it from the beginning, he said. He made sure to talk about the community that have been, working on the real world applications really since the mid-1990s.
Well, Flora, let's leave it there for another year. Thank you so much for joining me as always. And listeners, head over to the show notes where you can find links to all of Nature's coverage of this year's winners.
And that's all for this week. As always, keep in touch with us on X. We're at Nature Podcast. Or send an email to podcast@nature.com. I'm Nick Petrochow.
And I'm Benjamin Thompson. See you next time.